Okay, in our next example, we're going to look at Galois groups of nth roots. And we kind of already saw that in the previous example where we looked at a square root of -1, and we found the Galois group was cyclic of order 2. But we can actually do a little bit more without much machinery. We can compute Galois groups of adding nth roots to Q. So let's do an example of that real quick with a very specific nth root. So let's let alpha equals cube root of 2 be the real cube root of 2. Remember, there's 3 cube roots of 2. There's cube root, the real cube root, and then omega and omega squared times the cube root of 2, where omega is a primitive cube root of unity. All right, so by work that we've done before, oh shoot, I think I need to use this color. By work that we've done before, we know that if, oh shoot, we use alpha. Let me use C as in the book. If alpha from Q adjoins C to Q adjoins C is an automorphism, then alpha of C cubed is alpha of C cubed is alpha of 2, because C is a cube root of 2, but alpha fixes Q. Every automorphism of an extension of Q fixes Q. Okay, so whatever alpha of C is, it must go to a cube root of 2. So alpha must send C to a cube root of 2, because when we cube alpha of C, we get 2. Great. Now, how many cube roots of 2 are there in Q adjoins C? Right? How many cube roots of 2 are there here? And the answer is 1. And the reason for that is simple. Q adjoins C is a subset of R because we took Q, which is a subset of R, and we added in C, which is a real number, so we can't ever leave R. And the other cube roots of 2 are complex. So there are no other cube roots of 2 here because they're complex and we are a purely real field. Great. So what this says is that alpha has to send C to the only cube root of 2 in Q adjoins C, and there's only one, it's C. There are no others. All right. Well, since alpha of P plus QC plus RC squared is what? We have to break up under addition, and then we break up under, well, we know that PQ, R, and C, R and Q rather, sorry. For PQ, R, and Q, alpha of P should be P because it fixes Q, and then this one should break up under multiplication, and then this one should break up under multiplication and also exponents because whole exponents are repeated multiplication. So that's P plus Q. We just decided that alpha fixes C, and then we just decided alpha fixes C, so it must also fix C squared. So the only automorphism appears to be the identity. So what this tells us is that the Galois group of Q adjoin the cube root of 2 over Q is trivial. It's the trivial group. It just has the identity. And sometimes we write 1 for this to indicate there's only one thing in it, and it's the identity. All right, cool. So that's a cube root example, and it relies on the fact that the other roots of the cube root of 2 are complex. Let's do another example. Let's let, in this case, D be a fourth root of 2. And there's actually 2 of them. I'm taking the positive one. right? Because the negative d is also a fourth root of 2. And let's let alpha from Q adjoin D to Q adjoin D be an automorphism. It automatically fixes Q, so I don't have to say that. Then again, alpha of D to the fourth is alpha of D to the fourth is alpha of 2 is 2. So alpha of D must be a fourth root of 2. Now, as a quick reminder, the fourth roots of unity are 1, I, negative 1, negative I. And so in this case, when we multiply by the fourth roots of unity, when we multiply by I and negative I, we are going to leave the set Q adjoin D, because Q adjoin D is a purely real field. However, when we multiply by negative 1, it's going to be a new fourth root of 2. So in this case, negative D belongs to Q adjoin D. So alpha of D could be plus or minus D, but it can't be any of the other ones. It can't be I times the fourth root of 2 or negative I times the fourth root of 2. And so we get two possible automorphisms. The first one is the identity, which arises by alpha of D equals D. And the other one is, I'll call this one, I don't know, sigma. Sigma of, let's see, we have to go to P plus QD plus RD squared plus SD cubed, right? We have to go all the way up to the cube of the fourth root of 2. Is going to arise by letting D be negative D, or sending D to negative D. So it's going to fix P and it's going to fix Q, but it's going to send D to negative D. It's going to fix R, then it's going to send D to negative D. It's going to fix S, and then it's going to send D to negative D. So we get P minus QD plus RD squared minus SD cubed. And again, I write possible because we haven't actually checked that this defines an automorphism. However, we can easily do that. Now we've actually proved a result that shows that if you have conjugate roots, there's an automorphism sending one of the roots to the other. And that's fine. I like to remember minimal polynomial stuff though. So sigma is an automorphism by the composite. All right, we can take Q adjoin T and we can mod out by T to the fourth minus 2. We can evaluate at T equals minus D to land in Q adjoin minus D, which happens, of course, to be the same as Q adjoin D, because if I alter by a negative, I haven't left the field. That's plugging in T equals negative fourth root of 2. And then we can undo evaluation at D, which is also an isomorphism. And so sigma arises as the composite. I first undo plugging in D, and then we plug in negative D. And of course, that's going to send D to T, and then T to negative D. So this is going to send D to negative D. Okay, so that's fine. These automorphisms we've constructed, these isomorphisms we've constructed already, and this is an isomorphism between a field and itself, and that represents sigma. Okay. All right, so this video is getting a little bit long, so let's state the general result and a reason why that's the general result. So let's let P be a prime. I'll write it as a theorem. P be a prime, or any dth root free or nth root free number, but I'll just state it for primes, and n bigger than 1. Then, well, I guess it's even true for n equals 1. Anyways, we'll put bigger than 1. Then the Galois group, then for any, then the Galois group of Q adjoin the nth root of P over Q. Oh, sorry, here I didn't conclude. The Galois group of Q adjoin D over Q has two elements. It has the identity and the interchanging the root with its negative. The Galois group here is going to be the trivial group if n is odd, and it's going to be Z mod 2 if n is even. And of course, I don't mean equals, I mean isomorphic too. Okay, and the reason is, so proof idea, if n odd, only the nth root of P is in Q adjoin the nth root of P, and no other nth roots of P. So it must fix it. And so it must be the identity, any automorphism. If n is even, plus or minus the nth root of P is in Q adjoin the nth root of P, are both nth roots of P. And so there's an automorphism that will negate when n is even, and the negation is not an automorphism when n is odd. And that's roughly what happens.